All right. Let's do stuff. Now let's get my old-fashioned notes. Since I'll just deploy it, right? Really, I just like didn't prep anything for this lecture. I'm just trying to like run out the clock with technology problems.
50 minutes of setting up the camera.
Right, yeah.
Oh, well, looks like we're out of time.
Looks like we got this over here. Okay. No, I actually did prepare something. But now I'm probably going to get through it. All right, marker, thing, notes. Cool. All right. Now we're actually ready to have class. And it is recording. Let's double check. Ooh, actually, it might not be recording. No, it's recording. All is well. Okay. Does anyone have any questions, comments, concerns before we get started? No, you haven't missed anything. We just haven't had a homework assignment or a project in the last week or so. We'll get that changed this week. We'll get you some practice problems to do on Wednesday that involve what we're going to talk about today. And we'll do a new Python project for sometime next week. So today what we're going to talk about is we're going to kind of close the book, so to speak, on the Z transform by finally tying it back in with our LTI system. So we're going to call this lecture the Z transform. And LTI systems. And yeah, we're actually going to live with those auto-focused issues. Okay, so remember our basic definition for an LTI system, which is that we've got some output signal Y. That's a sequence of N, and it's equal to our input sequence convoluted with our impulse response. And the reason we like the Z transform is because it lets us get out of having to do convolution, right? We can just say that Y is a continuous function of Z is equal to the Z transform of X times the Z transform of H. That's all there is to it, right? So what we're going to do is we have an impulse response and we have an input sequence. We just take the Z transforms, multiply them, take the inverse Z transform. Because that's how much we hate doing convolution. So let's take a look at what that plays like. Actually, I think I can go into here. Let's work out a little example. Let's say that we've got two finite sequences. We'll say that they're x1 of n, and that's equal to delta of n plus 2 delta n minus 1 plus delta n minus 2. And we've got another thing, x2 of n is equal to delta n minus delta n minus 1. And we want to find y of n, which is the result of convolving these two signals. And we could do convolution the long old-fashioned way, but of course the point of this exercise is that we're going to do it with the Z transforms. So all we do is take the Z transforms of both of these guys. Let me erase that, give myself a little bit of room. And we'll say that the Z transform of x1, right, we can do this piecemeal just kind of by inspection, right? The Z transform of the delta.
We can't see.
What's that?
The stream is exploding.
It's paused. Why is it paused? All right, let's just try this. Let's see what happened. just wanted to do class, man. All right, can you see it? Can you hear it? Have we all gone away? All right, again, we're just going to power through. It is recording, so if for some reason it keeps being weird, then we can always watch it on YouTube after the fact. So hopefully it stays with us. And if something happens, just like speak up. I'm not going to turn around to look at the text, so I don't know that anything happened until you speak out loud. Okay, let's get back to it. So where were we? Right, we had our two functions, x of 1, which is just these train of delta functions, x2, which is also this small train of delta functions, and we wanted to take the z transforms of these guys, so we can do it by, and because they're delta functions, we can do it by inspection, right? The z transform of delta n is just 1, plus the z transform of 2 times delta n minus 1 is going to be 2 times, all we do is z to the negative 1, plus the z transform of delta n minus 2 is just going to be z raised to the negative 2. We love delta functions, man, they're easy. And the z transform of x of 2 is just going to be, again, 1 minus z to the negative 1. Pretty easy. All right, let me kind of raise the top here to give myself some more room. So now what we want to do is multiply these guys together, and then take the inverse z transform. Well, this is an old school whiteboard, not a glass board. Didn't it used to be a glass whiteboard in here? Whatever. Okay, so now y of z is just going to be the multiplication of these two guys, right? So we'll take quantities 1 plus 2z to the negative 1 plus z to the negative 2, 1 minus z to the negative 1. From here it's just algebra, multiplied out. Let's do the, do one at a time, so we'll just have what, 1 plus 2, z negative 1 plus z to the negative 2, now times negative z1, so that's going to be minus z to the negative 1 minus 2z to the negative 2, right? Z minus 1 times 2z minus 1 is 2z minus 2. And then finally we'll have minus z to the negative 2 times z to the negative 1 is going to be z to the negative 3. We'll simplify a little bit and get what? Let's see, we got just 1 by itself, 1. Let's put them all together. 2z minus 1 minus z minus 1 plus z to the minus 2 minus 2z to the minus 2 minus z to the negative 3. And we get that y of z is equal to 1. 2 minus 1 is just going to be, so 1 plus z to the negative 1, z to the negative 2 minus 2, z to the negative 2 is going to be minus z to the negative 2 minus z to the negative 3. And we can do the back end by inspection. Or rather, I should say, Now we're going to take the z transform, or the inverse z transform, excuse me, to get our y of n, our discrete time sequence. And again, we can do that one just kind of by inspection, right? The inverse z transform of 1 is just delta n plus the z transform of z to the negative 1, or the inverse is z of n minus 1. Negative z minus 2 is going to bring us to minus delta of n minus 2. Negative z to the negative third is going to be minus delta of n minus 3. And there we go. There is our solution. Any questions about that? Should be pretty straightforward, right? Especially for an example that's just filled with delta functions. Right? Take functions, z transforms, multiply them, inverse z transform. Wash, rinse, repeat for all of eternity. All right, so let us do a more interesting example. Give me 2 seconds while I. Where it says, yeah, I think they replaced this whiteboard with a worse whiteboard. Because this is like an old-fashioned one that like bleeds. Not a glass one.
Now you gotta get a bottle of solution.
That's what I'm saying, yeah. Maybe they thought that was like, maybe everyone was having that like auto-focusing problem. Maybe they thought this would be the solution to that. Because, yeah, that's gross. All right. So, let's do this one. Find y of n equals, of course, x of n convolved with h of n if x of n is equal to some constant a raised to the n times u to the n. All right, this is one we've seen a whole bunch, so it's just some exponential. And h of n is equal to another constant. Gross. Just a, capital A, times u of n. All right, so let's see. Let's start with getting our z transform of x. Now we worked through several examples involving this sequence. So hopefully what we know now by inspection, or we recognize this by inspection as just 1 over 1 minus a times z to the negative 1. And y of z equals the z transform of a times u of n, which we haven't seen this one as often, but it's very similar. It's just going to be constant a over 1 minus z to the minus 1. And we've got here our region of convergence. The absolute value of z must be greater than a. We're familiar with that one. And then here, the absolute value of z must be greater than 1. Nobody's going to comment on the fact that I wrote y of z there. And that should have been capital H of z. Because now we need y of z. It's going to be x of z times h of z. It's going to be 1 over 1 minus a z negative 1 times a over 1 minus z to the negative 1. And we kind of leave it right there. Right? We can simplify a little bit to say it's equal to a over 1 minus little a, z to the negative 1, and 1 minus z to the negative 1. which means that we've got a 0, excuse me, if we rearrange it, we would have this, right? A times Z over Z minus A and Z minus 1, which means that we have a 0 at Z equals 0 and poles at Z equals A and Z equals 1. Now the region of convergence here is going to depend slightly on whatever the value of A was, right? Because remember that if the region of convergence is greater than whatever those constant values are, then the region of convergence starts at the outermost one. So that's a 0, and that's a 0. Let's say that that is 1, and that's A. Well, so the 0 is 0. Our region of convergence is all of that outside of A. And in fact, it has to be this. Does anyone recognize why? We actually couldn't do it with A being outside the 1. Why is that? Yeah, so A has to be less than 1. Why does A have to be less than 1, Cole? Exactly, right? Otherwise it wouldn't converge. Because even if we go all the way up here, right? Remember, everything has to converge. Everything has to have a finite response. And A of n, in order to make this whole thing converge, has to be less than 1. Good deal. Okay. So now we've got that. And we need to find the inverse Z transform to get back to our sequence Y of n. So let me make some room for myself. All right, let me say this. We're looking for Y of n, which for us now is the inverse Z transform of A over 1 minus little a Z to the negative 1 and 1 minus Z to the negative 1. So what method are we going to use to solve this inverse Z transform?
Power series.
What's that?
Power series expansion.
Power series expansion. Well, I guess we could if we really wanted to.
Take the scenic route.
What's that?
Don't just take the scenic route.
Take the scenic route, yeah. Yeah, we could do that long division and do our power series and figure it out. I'm going to go ahead and say, let's use the partial fraction expansion method. Despite the fact that it seems to scare everybody, is arguably easier. So the first thing that can happen is A can just come out, right? Because A is a constant. And we can just say, who cares about big capital A? So yeah, so let's make a note here. We're going to use partial fraction expansion. So let's say we have A times our continuous function y is a function of z. That's going to be 1 over 1 minus little a times z to the negative 1 times 1 minus c to the negative 1. And we're going to break that out. We're going to find our two constants. A 1 over 1 minus a z to the negative 1 plus a2 over 1 minus z to the negative 1. Let's find a1 first. So a1 is going to equal to what? It's going to be just 1 minus a z to the negative 1 over 1 minus a z to the negative 1 times 1 minus, not a, z to the negative 1. All of that where z is equal to a, which is going to get us, these two quantities cancel out, 1 over 1 minus a to the negative 1, which translates to a over a minus 1. And we can leave it right there, so let's just write it up here. Let's say that a1 equals little a over a minus 1. Any questions about having it down? And let's say that a2 now is going to equal 1 minus z to the negative 1 over 1 minus a times z to the negative 1 times 1 minus z to the negative 1 evaluated at z equals 1. Which will equal, these quantities will cancel, 1 over 1 minus, oh, did it wrong. Not that one. That's what I get for rushing. That one. So that'll be 1 over 1 minus a times 1 to the negative 1, which is going to be 1 over 1 minus a. Cool. All right, so a2 is equal to 1 over 1 minus a. So now, let's say we drop everything in. And we have that a times yz is equal to all of this mess, a over a minus 1 over 1 minus a z minus 1 plus 1 over 1 minus a over 1 minus z to the negative 1. Now we're going to do a little bit of algebraic gymnastics here and say that y of z, I'm going to factor out 1 minus a. So y of z is going to be equal to a over 1 minus a. Let me drop that down just a little bit. A over 1 minus a times, so that's just going to be this one straight up, 1 over 1 minus z to the negative 1. Now when we factor out 1 minus a, what'll happen here is it's negative this one, right? So it'll be minus a over 1 minus a z to the negative 1. So, give myself a little more room. Now we do it by inspection. And it's sort of what we had in reverse there, right? So y of n is equal to whatever this is, big A over 1 minus little a, times the inverse z transform of 1 over 1 minus z to the negative 1 is just u of n from the table, and that's going to be minus, well, a over 1 minus a z to the negative 1 is going to be a times a to the n times u to the n. And we could leave it there, but just for the heck of it, we'll simplify some stuff, and we'll say that our final results yn is equal to big A over 1 minus little a times 1 minus a to the n plus 1, all of that times u of n. So there we go. All right, any questions about that one? Like a lot of these, they're just kind of long and tedious, but not like ultra complicated. Let's do one. Oh, we lost all kinds of time. All right. So finally, let's bring it down to one of the first things that we talked about, which is linear or discrete time LTI system represented by that difference equation, right? So let's see, LTI system represented by this guy. Series from k equals 0 to n of a of k times y to the n minus k is equal to k equals 0 to b m of b of k times x to the n minus k. So as an example, let's say that we have y of n is equal to constant a times y of n minus 1 plus x of n. And you're asked, what is h of n? What is the impulse response of the system represented by this difference equation? So that's what we're going to do. The first thing you have to do is you want to rearrange it to get it into this form. So we'll do that. We'll say it's y of n minus a times y of n minus 1 equals x of n. Then you do this bizarre step. Remember, all the y's become h's, and all the x's become deltas. So you perform the substitution. H of n minus a times h of n minus 1 is equal to delta n. Let's make some notes here. That's what we'll take to call the substitution step. Next step, you're going to take the z transforms of all of these guys. Some of this is pretty easy. The z transform of h of n is just going to be big H of z minus a times, so if it's time shifted, so n minus 1, first we have the constant little a. The n minus 1 gets us z to the negative 1 times h of z. And the z transform of the delta function is just 1. Now we solve for h of z. Let's just say that that's our z transform step. Now we solve for h of z. That'll give us what? H of z is equal to 1 over, look at that. It's almost like we planned it out this way. 1 minus a times z to the negative 1. So solve for h of z. And then finally, we take the inverse z transform. H of n. We can, of course, do this one by inspection because we've done this about 10 billion times now. That's just going to be our a to the n times u to the n. So h of n is equal to the inverse z transform of h of z. Cool. All right, any questions about that? Let's see, just a recap. What did we do? We talked about basically 3 different examples here. The first one we did was a finite sequence. Convolution, right? That's the one where it was just all a train of impulse sequences. 2 there, we did a partial fraction expansion method. And then this last one here was our difference equation. So it's 3 different forms of basically the same problem, which is try to avoid doing convolution.
Can you convolve a finite and continuous sequence together?
Can you convolve a finite and continuous sequence together? Yeah, absolutely. In fact, that's what we're going to do most of the time. Most of the time in practice, our impulse responses, our h's, those will be finite sequences that will convolve with x of n, which is a, continuous sequence. Right, so if you run like an audio filter, right, that audio signal is continuous, right? It's going to be constantly streaming, but whatever, thing you put upon, whatever filter you put on top of it, that will be a finite sequence that you'll essentially just pass the continuous time signal through, or the infinite sequence through. Cool. All right, any other questions? All right, on Wednesday, we will get into the next chapter, which kind of switches gears. We're going to talk about some more practical stuff. We're going to put I'm going to say we're not going to put the theoretical stuff away forever, but we're going to talk about sampling and how sampling affects the signals. We're sort of making our way towards actually being able to do the stuff. So we are done with the Z transform. Cool. All right. In that case, thank you so much, guys. I'll see you all on Wednesday.